All right, I've got 45 slides here. Now, that sounds like a huge amount, but I'm a very highly visual person. I've worked very hard to create a lot of graphics so that the information that you're going to see is very apparent rather quickly, so we don't have to spend a lot of time on each slide. But the format's going to be the first 15 slides or so are pretty much the ones that get us from where we've been in the past to the new approach. And then the remaining are taking that new approach and applying it to several amplifiers and just comparing them so we can observe just how important the additional information is that we've never really looked at before. So this is,
Bob,
yes.
how much of your presentation was triggered by the Peterson's presentation a couple of weeks ago or a week ago?
I've been working on this distortion measurement thing for several years.
Okay, great, thank you.
I just haven't been, I wasn't in a position to really come forth with it because as long as I was working for corporate, you get muzzled. A lot of people who've worked for corporate understand that you're limited in what you can say or what you can do. The human resources and the communications department pretty much want to see anything you may say, even though you're saying, I'm presenting it on my own, I'm in the AES, but they say, yes, but you work for a major corporation, and so we want to see what you're talking about. We want to review everything that you've done. And then they, of course, want to go through it and see if there's patentable stuff there. So until I was kind of freed from those corporate policies, I couldn't really talk a lot about this, but I've been working on it for a long time. So distortion measurements, a new approach. And what I'm going to do is I'm going to go through just a little bit of history and things that are very familiar to you, and then we'll make our way into the new territory. So this is what we're going to do. We're going to look at some traditional published specifications, a very brief review of historical information, relevant operating levels. This is kind of important because my research is focused on headphone amplifiers and headphones, personalized listening stations, and this is different than running large sound reinforcement systems, and these relevant operating levels are extremely important to know. Then we're going to decompose THD plus N. This is the classical measurement that has been used for time out of mind. We're going to decompose it and see why it's a lossy compression applied to a measurement. And then the new visualization concept. This should take about 15 or 20 minutes to go through that. Then the rest of it is pretty much looking at the multiple amplifiers being examined using this.
I forgot to ask you if you want people to ask questions as you go or hold them till the end.
What I'd like to do is I'd like to get from this point down to where we introduce the new visualization concept, because I have a feeling everybody here is well familiar with this. They just probably haven't heard the story told this way. And when we get to this point right here, the, what is it, 1, 2, 3, 4, fifth bullet down, I'll pause right there and then we can go back. So that's about the first 15 slides.
Beautiful, thank you.
And then after that, yeah, it's pretty much, it becomes a discussion. So here's an example of a specification. This is for, what is it? It's a iFi Audio IDSD Diablo. And if you go to their website and look at their stuff, you're going to be greeted with lots of colorful pictures and buzzword bingo. In spite of all that, they actually make a decent sounding all-in-one DAC amp. This is a dongle that you plug into your laptop or personal smart device and gives you the D-to-A converter and the amplifier. You'll notice though that we're going to talk about THD plus N, that traditional measure, and all they tell you here is it's 0.002% when you use the balanced output or 0.001% when you use the single-ended output. What's missing from here is the level at which it was tested, the frequency, and the load. Typically, these folks use 2 volts RMS as the level, and 1 kilohertz has been the traditional measurement. Actually, I think it's 997 if you really want to be a stickler for the tradition. But 1 kilohertz and 2 volts RMS. And the 2 volts RMS has come about because people who have become self-appointed gurus on the internet who have some money bought themselves a bunch of APX 555s. I say one per person, but there's multiple people who've done this. And the APX 555 happens to have a sweet spot and a cheat mode that gives the measurement system the ability to have the lowest distortion measurement capability of any analyzer out there. It's really ridiculously low, but it only works at 1 kilohertz, and it only works in this cheat mode. And if you go through and look at the APX 555's distortion, the generator distortion characteristics, 2 volts and 4 volts RMS are where it works the best. And so you can measure all these various things out there, and the headphone amplifiers being included. We're going to show you why 2 volts RMS is not a great place to be measuring that. So this is not a very complete specification, but there it is. Here's another one. This is a little more complete. This is a DSH A3FN. It's made by Niche Audio. Actually, it's designed by Doug Savitsky. I know these people. And this one is a little more complete. We tell you that it's done at 1 kilohertz, give you the loads. And what's missing is the level. He forgot to put it up there. I know that this was tested at 0 dBu, 0.775 volts RMS. I know because I'm the one who provided these measurements and then calculated margin on the measurements to these folks for them to publish these specs. So here we see 0.02, 0.015. We might as well call it 0.02 for both, and compare that to our 0.002, an order of magnitude lower. That's the way you typically see total harmonic distortion noise. Total harmonic distortion noise has been measured since time out of mind because it was one of the easiest things to ever measure. You put in a 1 kilohertz signal, notch it out of the output, and whatever's left over is the distortion. But I'm going to point to this book. It's the Radiotron 3rd edition. I have this book. And in this highlighted area, the total harmonic distortion is not a measure of the degree of distastefulness to the listener, and it is recommended that its use should be discontinued. Asterisk, down here asterisk. Combination Tones and Nonlinear Systems, Electronics, September 1938. 1938. That's a long time ago. We recommended this should not be done, and yet it's still done today, partly out of tradition, partly out of ignorance. Look at up here. Is there a mouse pointer going around on your screens? When I'm pointing up and
yes,
yes, we see
a
it.
Mouse. Okay, good. Look up here. They were already thinking of 2nd, 3rd, 4th, 5th, 7th harmonic, and they had specifications for what they considered good fidelity: 5%, 2.5%, and for a lesser, they were allowing 10%. 10% is still the distort THD plus N level. If I'm a designer and I'm doing a little built-in audio thing on a medical device or some other device, and I go to TI or Burr Brown or whoever and look at their op-amps, they'll show me a curve, but they'll also typically state the 10% total harmonic distortion level. It's kind of things that have been going on for years and years and years. But I'll finish this little spot up where it says, it is always preferable to specify each harmonic separately. That's really important. So it's been known since 38 that THD plus N was probably not a very good thing to do. However, THD plus N is still used in its form of SINAD, which I'll relate those two in just a moment. So moving on, operating levels, especially when you're interested in headphones. It's kind of nice to know how much sound level do you get out for how much voltage or current power that you put in. And here's a chart of some really popular headphones for both high-end listeners and also utility use in the studio. And you can see that if I put in a minus 20 dBu signal, and minus 20 dBu that's 0.0775. We're talking 77 millivolts. These are the sound levels we typically get at 1 kilohertz. This is the 1 kilohertz sensitivity. And looking at a number of these things, we can see a range, except for the in-ear monitors, which are usually very sensitive and go much higher into the hundreds of dB for this level. We're looking at 82 here for a biodynamic T1, 90, almost 100 for the LCDX MX4. My favorites in this whole batch are Sennheisers. I really like Sennheisers. 81, 80 for 650, 600, 800. But you get the idea that between 80 and 95 dB SPL is a pretty good range to be thinking what you're going to get out when you put in a 77 millivolt signal. Now, conversely, if you're putting in 2 volts, you're in the place where you're going to be putting these things, most of these, into the 120 dB SPL, and these guys here under the 140, and you're likely to burn out voice coils and things. So I'm kind of leading up to that's not a good level to be working at when you're characterizing a headphone amplifier for headphone use. Now, we always talk about the nominal impedance on these things, and so it's important to remember that, well, if you got planar headphones, yeah, that nominal that is usually specified at 1 kilohertz, nominal impedance does stretch up and down. It's the same. But for most electrodynamics, you get a rise at the resonant frequency. And it's important to know that if you got 300 ohm impedance going in, you might rise up to 600 ohms. And the focal clear is one electrodynamic that has, it's at 55 and it goes up to 500 ohms at its resonant frequency. So that's an interesting load that one has to be mindful of on these things. So I'm going to be using THD plus N and SINAD pretty much interchangeably, and to a lesser degree going between percent distortion and dB. I like to work in dB because I like to know where we are. Here's a chart that kind of relates things. If you've got zero, if you put in your signal at 0, whatever the level is, and your THD plus N measures 0 dB below it, that's 100% distortion. And SINAD, of course, is the same. The signal noise is 0. So as we go down this chart, you'll see that THD plus N and SINAD are just the inverse of each other here in the sign change. 20 dB down, 40 dB down, 60 dB down for the THD plus N is a SINAD of 20, 40, 60, 80. So you just invert the sign and you go from THD plus N to SINAD. There's a formula that relates you between the THD plus N and the percent, but you get the idea here that every time we go down 20 dB, the percentage drops an order of magnitude. And so I'm going to be focusing on areas between minus 40 and minus 100 because that covers percentage ranges of 1% to 0.001% distortion. So this chart here relates these things. You know what? I will pause for a moment and say any questions so far on that.
I had one about your chart of sensitivity ratings for the headphones. Is that all your measurements there?
These are where it says nominal sensitivity. I've got a huge spreadsheet that's far more complex than this and won't fit on even the biggest screen you can imagine. I have made measurements, and most of my measurements are made with pink noise on a dummy head, and I come up with the sensitivities, which typically come very close to the nominal sensitivity that the manufacturer specifies. But on this particular chart, these numbers, you'll see these as being the nominal sensitivity published by the manufacturers. And then I've just gone through and done all the calculations of how much power we're going to get there and what sound levels we're going to get out. But yes, I verified a good many of these. And I own a good many of the headphones on this list here.
Excellent.
And of the Sennheiser HD800s, I own many custom modified variants of it. You can probably guess that that headphone is one of my favorites. Anything else? Okay, then we're going to move on into taking the THD plus N and decompose it. Now, in this particular case, I am doing a ridiculous measurement to make a point in another slide, another presentation I was doing. I was testing a hybrid amplifier. That's where you've got a tube input stage and a FET output stage as an example. And this particular amplifier, I was running it at plus 20 dBu. That's a ridiculous level. Headphones should never be run there. But this is the number right here. This 2.22% THD plus N is what's being output. And that's when you take, in this spectrum here, there's our 1 kilohertz. You notch that out, and everything less is what produces this number. Well, now if we start to say, let's break it down like it was suggested in that Radiotron edition, specify the harmonics separately, and with today's modern analyzer, this is a piece of cake. We couldn't do this even 50 years ago very easily. So here's our second harmonic. You can see the second harmonic is 2.32. It's the dominant contributor to the total harmonic measurement. Here's the third harmonic. It's considerably less. Then in this red box is all the higher harmonics, fourth and on up. In this red box over here, we've got all the AC mains noise and some non-harmonic noise. And then in these little red boxes here, we have all the inharmonic noises as well. This particular measure here is one I came up with called 4 plus HD plus N. So we take the fourth plus harmonic and up and all the noise and make a measure of that. But even that's still too much simplification, because this harmonic distortion here has a different effect when you think about the Fletcher-Munson curves, the isocontours of equal loudness. Harmonic distortion up here has a greater influence on what our assessment of distastefulness, as opposed to AC mains noise down here. If you take the whatever your AC mains is, 50 or 60 hertz, and then take the fundamental plus the first 4 or 5 harmonics, those are going to usually be much lower. And when you think about the isocontours of equal loudness, which I think I've got in here somewhere, no, I don't. They are often not a contributor to something that we perceive, unless you've really got a bad case of hum. This noise right in here, which is right in the sweet spot of where our ears are the most sensitive, noises here at very low levels can be very intrusive. So while this breaks it down for you into second, third, and the higher harmonics of the noise, it's still an oversimplification. Now, thinking about those amplifier specifications we saw where we took the percentages off of their spec sheets, and then we convert them into dB so we put them on a SINAD chart. This is commonly done on numerous audio-oriented websites around the web, and they like to rank things like this and say the amplifier SINAD at 2 volts RMS, 1 kilohertz with some load. They often don't specify the load, and they'll put them in a bar chart like this. And of course, if you're the kind of person that just likes to have a simple world view and you compare them, you say, well, gosh, this has got the best SINAD. It must be the best sounding of the three. I'm going to say not so fast. It's not that easy, but this is done, and it galls me a lot. Part of what motivated me into doing this kind of work. So keep these 3 levels in mind in this presentation view.
Bob,
And I'm going to, yes.
There was a question about what does SINAD stand for?
Signal, noise, and distortion. So SI is signal, noise, and distortion. So
Thanks.
THD plus N and signal, noise, and distortion, they're just two ways of looking at the same information. Anything else? Okay, let's set the stage for going to something bigger. When we take and look at 1 kilohertz at 2 volts RMS, 2 volts RMS turns out to be 8.23 dBu. So that's where we are. So we're up here. This is level on this axis in dBu. This is frequency, low frequency here, high frequency here. And we've got distortion going from minus 100 dB to minus 40. Remember this is 1% distortion, 0.1, 0.01, 0.001 down here. And I don't figure it's worth worrying about things below that. And we draw a little line here where we would make assessments if we used SINAD alone or THD plus N. We're limiting our universe of distortion measurements to this little red line here. Now this is drawn in this 3D graphic to kind of help amplify that we're not taking a very big view of the distortion on this amplifier and trying to make an assessment on it. This is like the classical blind men and the elephant story. So I'm going to move us to taking the first amplifier that I did this to and said, here's that DSHA3F THD plus N surface. We have swept across frequency, we've swept up and down levels, and this is the distortion surface. And then what's projected down below is a heat map of that, because the surfaces are cool to look at, but when you want to compare two amplifiers, A/B them, then I'll take and produce a heat map that's a 2D map, and they're always the same size, always the same aspect ratio, always the same levels everywhere. So you can flip back and forth between them and compare and say, this is how these amplifiers compare. You'll notice here that the little red dot would be our 2 volt RMS, 1 kilohertz assessment. There's a lot more going on in this amplifier than that little dot would let you know about. And in particular, those of you who are familiar with transformer inputs on devices will recognize that there's a certain rise here, and this is due to the input transformers on this particular amplifier. I will also caution you not to say, oh, this is bad or good on these surfaces. We're still investigating what do the distortion profiles look like on something that sounds good versus something that sounds bad. Now, I haven't gotten to my collection of bad sounding amplifiers in the laboratory yet. This is one of my favorites, and it surprised me at how wild its distortion surface was. So remember, THD plus N, though, is still a considerable reduction in information. So later, I'm going to break down the surfaces into the D2, the D3, and the 4 plus HD plus N. And remembering that I have yet to get to programming my analyzer to break that further down into AC mains noise only and all other noise. So that's future work. This is time consuming. I've managed to work out automation on my D-scope. Graham Boswell was a brilliant designer of this D-scope in allowing us to have software access to the analyzer that allows you to expand into what you would like to do rather than handcuffing you with just whatever measurements they provided for you. The APX 555 is not as flexible of a machine, which is one of the reasons I went with the D-scope instead of, prior to the APX 555 was a 535, 525. Anyway, I went with the D-scope because it was far more flexible for the research I wanted to do. Uh, I'm going to now move to taking the 3 classical measurements we made at the beginning. I've animated them here so you can see this is how your universe of what you know is about them based on that classical measurement. Now I'm going to show you 3 surfaces from the 3 different amplifiers. The one that we haven't talked about before is the Molnar 3. But you can see you don't have to remember the specifics of this, but look at the differences in those distortions. By the way, all 3 of these amplifiers are considered by listeners who have heard them and compared them some pretty good sounding amplifiers. So there's something special going on in each one of these 3, and we'll break that down a little bit as we go. Welcome to a universe of much more information about distortion in amplifiers. That's a lot that I've just presented. Questions at this point?
This is amazing.
This is time consuming too. Oh, that's what I kind of wandered in my thought there. I've programmed my D-scope to be able to do the data collection pretty automated, going through the levels, the frequencies, and catching the distortions. And that takes it about 20 minutes just to capture the data. Then I have to take the data and catenate it externally. And then from the catenation, I take it through a trip through Excel to organize it and get it put in all the right format before I take it into this plotting program I use called PSI Plot, which PSI Plot, then I'd create a template for it. And the template allows me to keep all of these axes identical. Now you'll see a little bit of a flip on the numbering here because I did do some of these at different times. So you'll see some stuff moving around here, but the plot itself, the graph, is kept identical so that A/B comparing these things in the future will be much easier, both in the surfaces, and I've got contour map outputs as well. And I have this favorite watermark of mine that I've adopted on several forums. I'm known as Atomic Bob, and I use this mushroom cloud, atomic explosion in a skull shape as my watermark on these. Because in the past, when I would put stuff up on forums, I would discover my work on other forums with no credits given. So I've kind of learned to put something on there that's pretty obvious to spot.
Can I ask a question here?
Yes.
The bottom colored part seems sufficient on its own to tell you, to be able to compare the different amplifiers.
Yes, it is.
But the combination of the bottom plot plus the big blanket of different shapes is more, and maybe it's because I'm not familiar with seeing just the bottom colored part.
Oh, the intent is to have both available, but when you want to compare them, it's easier to take the heat maps and compare them. You're going to see some heat map presentations a little further on here. Like I say, where are we at time? It's 4 o'clock. Yeah, I expected the bulk of it was going to be the first 15 slides, and then the rest of it we're just going to do comparisons. But let me show you why the surface maps themselves. You can do a fair amount of comparison with them. The heat maps, though, I think are a little easier for another visualization I'm about to introduce shortly down here. I think we're about 5 slides away from that one. So let's take and go back. This was the THD plus N. And remember I said this is still an oversimplification. So we're going to decompose that. Here is the 4 plus HD plus N surface for this amplifier. There's the D2, the second harmonic distortion. I call second harmonic D2, distortion 2. D3 will be third harmonic distortion. You can see the transformer behavior in this particular amplifier by these plots. And they give you, these three tell you even more. And I'm going to flip back and forth just so you can see how different they are. And there was the total, and you can see that gave you an idea, but it's breaking it down that gives you yet more information as to what's going on with this amplifier as we look into second and third harmonic, and then all the rest. And like I said, all the rest, future work will include breaking that down further too. So for right now, I tend to still look at this one and know it's still an oversimplification.
That one and the next one in the series, the others, all the other plots are single planes of various shapes, but this one is dipping down to 0 and then coming back up.
Correct.
And what does that tell you?
This one tells me there's a transformer in the path, and
Okay.
that transformer, as we hit low frequencies, notice where it's really coming up, about
Yeah.
800 hertz. Here's the rise. Now remember, this is 1% distortion up here, so this is 0.1% distortion at about -60. And so when we get to really low levels and low frequencies, that transformer is having a fair amount of influence in the coloration of the signal going through. And in third harmonic, here on the second harmonic, it's actually as you get to higher levels that the second harmonic has more influence on it. But yes, you were correct in looking at that and saying you didn't get that from this plot here.
Not at all.
That's why. And remember our fellows back in 1938 saying it's really preferable to specify the harmonics separately. Gosh, weren't they right? It's important to take a look at these books and realize just because it's old doesn't mean it's out of date. That Radiotron third edition, I think I paid $15 for it to get it from a used bookstore in really good shape. It's got a lot of my double E courses all very succinctly encapsulated in this one book. It really is a treasure. So this is where we're going to go now from this surface and look at this contour map down here. We're going to just look at that contour map alone right here. This is that contour map for the THD plus N. And this is easy to compare 2 or 3 amplifiers to visualize them. And here's our color legend. As we go to orange, that's higher distortion. As we go to deep purple, it's low distortion. Also, just to hammer home, the traditional measurement point of 2 volts RMS is way up here. But this black box that we've put in here encloses the operating area that we are likely to be using when we listen to headphones. Remember those charts that we showed you for the SPL, and we said that -20 right here was between 80 and 95, depending on your headphones. Let's take the Sennheisers as an example and say, well, let's call this 80. So there's 75 dB SPL, and there's 90 dB SPL when we're listening to Sennheisers. That would be a pretty reasonable range to be listening in, provided we are listening to music that actually has some dynamic range to it. That's another topic for some other time. But this box is where we're going to be. So I'm going to break this. Is that what I do next? I break it down? Yes, I break it down first. It's kind of it's easy to bifurcate into 2 different directions at this point, but I'll break down the THD plus N to the 4 plus HD plus N for this amplifier. And you can see how even it is in this area. And then we'll also look at the D2 contour and seeing how, yeah, it's pretty wild. It increases at the low frequencies, but it's almost nothing at the high frequencies. And remember, always keep in the back of your mind the Fletcher-Munson curves, the isocontours of equal loudness, and think about the sound levels we're at, knowing that this follows a pattern that using those isocontours is going to be not apparent as what it's doing. This will be a little more apparent because the D3 will have a coloration. The third harmonic is going to color a bit down at these levels in this amplifier. However, a lot of listeners who are familiar with this amplifier really like what it does with the headphones. Oop. So we're going to take a leap now. This is the other direction we could go. Imagine the dynamic performance going on in this, when you're listening to music. All these measurements have been taken using stationary measurements, and we've put them all together in this field, this map. So let's superimpose actual FFT of music playing into this area to help visualize how we're transitioning through the different distortion areas. This happens to be an excerpt from Ode to Billy Joe, Jerry Vivino. I think it's about 2 minutes in, minute and 50 seconds or 2 minutes in, and looped for 15 seconds. This gives you an idea of something you've never really looked at before, is dynamic behavior of the distortion of an amplifier. We always can do these stationary things and usually limit ourselves to just a single dot like this, or maybe a sweep over a limited range. Nobody's ever really done this. Questions?
You looked at anything with a dynamic range of essentially a flat line, like a lot of the modern music?
Well, pink noise. I could put pink noise in there and leave it steady, and it's about the same.
Okay.
It's about as interesting to me.
You were listening to that kind of music. Why would you care?
Yes, and my interest in dynamic range reduced music like that is about the same as my interest in recreational listening to pink noise. I listen to pink noise a lot because it's useful for my measurements, but it's not what I want to listen to recreationally. And I'm sure a lot of you recordists out there can share a lot about that. Okay, from this point on, what we're going to do, we're about halfway through, and the rest of these are just going to be looking at the other amplifiers that were listed there and just glancing through their distortion surfaces and mentally comparing those with what you've just seen. So this will probably go fairly quickly. There's about 20 slides of this, and then I'll show you my lab of what it looks like where I'm working and the odd stuff that I work with. So any other questions before we scoot on through this? Okay, here we go. This is the iFi Diablo THD plus N, and its distortion surface is lower and even, but it's got this crinkle to it. And there's the red dot for our traditional measurement that we would have based our spec sheet off of. And again, showing you just how much vastly more information you've got here. Breaking it down, there's the 4 plus HD plus N surface. And you can see it's substantially similar. If I flip back and forth between these two, you can see that the 4 plus HD plus N is really the dominant contributor, the THD plus N, with just the exception down here where you see it flip down a little bit. As we go into the D2, you see D2 is, except at very low frequencies, has almost no contribution whatsoever. D3 is even less. Oh, it's another important thing to note is that the iFi, all three of these amplifiers we're examining, two of them, well, let's see, one has no negative feedback, one has extremely low negative feedback, and this one has 2 or 3 localized negative feedbacks in the chain. So they're all unusual, and they're not a typical cookie cutter, let's just build an amplifier, throw a whole bunch of global feedback at it, get the measurements down there to where they look really good at this one dot and call it a day. These have been, these amplifiers have been designed with a philosophy of measurements and listening, both incorporated in their designs. So there's the D3 surface. And now we're going to the contours. And again, I point out the limited information up there. Here's the Diablo's contours, very even across here. It's kind of, and I'm still getting my head around this because these measurements I've had in this form for maybe only 2 months. There's the 4 plus HD plus N, not too much difference between those two. Here's the D2 contour. The only place D2 even enters in is right where our ears get the most sensitive on the Fletcher-Munson curves, but still probably just in the thresholds of what we might hear, and you only with very dynamic music. D3, really even less so, but it's interesting to know what's going on down those levels. Now we're going to hit the Molnar 3. That's the amplifier that's sitting to the left of me right now, sitting on my stack of D to A converters. This is a relatively recent product introduction from a company called Schit. It's SCHIIT. They have a sense of humor. And Jason Stoddard is the designer. This has no negative feedback. It's a solid state device mimicking a single-ended transformer triode system. There, get all the right words there. And you can see that it's a very flat, even surface. It does start to rise back up here. So what's likely to happen is that we're running into the rails, starting to run into power supply limitations. Red dots are traditional measurement. But this is incredible how flat this surface is across the frequency and how it rises so uniformly as we go down. This is likely noise limited. And the noise is at a threshold that is going to be just below or more than below our threshold of conscious hearing. But it might, what I'm working with as a hypothesis now is it might be the ultimate dither. The noise being it's so uniform. And in fact, going to the 4 plus HD plus N, flipping back and forth, you can see that noise surface continuing. And the only thing that's bringing it up is the power supply rails that we're hitting when we get to a ridiculously high level. Remember, this most headphones, this should be about 100 dB sound pressure level. We don't have any business really listening up here. Not if you value your hearing and you want to have it for a long time. Here is the D2 surface. Now remember, this has no negative feedback whatsoever. D2 surface is way down there. Yep, there's the D3. That's the indicator that we were hitting the rails as we get into the limits of what it can produce for voltage. And so now the contours of the same things. Remember the contours of these, I'm sorry, the maps. Yeah, contour maps. Look how even that is across there. This is impressive. This is why it's still sitting on my bench right to the left of me, even though I've been listening to it for a couple of months now. Here's the 4 plus HD. Oh, let's see. I changed something here. That was a mistake. I got the I narrowed the range on the operating area. That should be down at minus 25. I didn't update that slide. I was going through corrections and I missed that. Yep, I did it for all the next three. Here's the D2 contour. It's very uniform and very, very low, as you can see over here. And D3, this is interesting. It's at really low levels, rises up a little bit. But again, these are things that nobody's ever paid attention to. So all those little subtle things that we worry about when we're listening to stuff that's in the spaces. You know, music has the signal and it has spaces too. There's the notes in the spaces. In the spaces of things, if it's not squished all to hell, things happen. So here we go with another dynamic visualization of that same Ode to Billy Joe on the Molnar 3. And where are we for time? Okay, good. We're really good on time. So Any questions? I'm going to move to one more kind of visualization that's a little easier to produce, but
Before
not
you leave
quite.
this one,
What's that?
before you leave this area, the amp just before this one, was that the Diablo maybe? There was uh,
This
one
one?
of, yeah, that one. Yeah, okay, sorry, go ahead, go forward.
Okay. Yeah.
One
It's
more.
the SHA3F and the Diablo and then the
Whoop, whoop,
Molnar.
whoop. Yeah, so go back. One more. One more. There. That little thing that looks like a bay or a harbor, the hook area right there. What's the deal with that? How can there be a hole?
Beats me.
Oh,
Let's go back to the surface and maybe that'll be um, see these crinkles? Oops, wait a minute. There we go. These crinkles.
oh yeah,
Take a look here and project up and look at the crinkles on. That's why I was saying this has a crinkly surface.
right.
But yeah, I've just developed a technique for doing this, and now part of while my ears still last is to measure these and listen, measure and listen,
Hmm.
and compare. And I can't do all the listening myself, so I have numerous people I know who have trusted ears and compare notes. I show them measurements, and we discuss them and try to wrap our heads around is in the past people have said, oh, measurements don't tell you a whole lot. And who was it? The fellow that used to work at Audio Precision, he came to give a presentation to us. I'm drawing a blank on his name. And,
Jonathan?
yes, Jonathan. That's the fellow. And one of the statements he says, not everything we can measure matters, and not everything that matters can we measure.
Hmm.
Well, I'm trying to push that what can we measure a little closer towards maybe having the ability to infer what matters.
Hmm.
Now, this is not the
So,
only thing. I mean, this is one thing I've tackled, but I've got other ideas too that I won't get into here.
so the crinkles are
Oh,
negative feature
we were.
and can create weird things,
Mhm.
whereas flat or smooth is better.
Oh, that remember earlier, I said I'm still wrapping my head around. These are three amplifiers who have been considered to sound awfully good. I haven't
Yeah.
tested any not so good sounding ones yet. So
I,
these are
I,
just.
I
Go ahead.
really don't understand why there's a concern about evenness or why it seems praiseworthy when a heat map is smooth going across it from low to high frequencies, as long as the distortion products or noise products are low enough that you can't hear them. Who cares whether they rise or fall a certain number of dB within a given octave?
Well, see, that's the thing that I've been trying to wrap my head around for a long time is, um, let's see, do I have, uh,
Plus, I
what,
think that equal
I've got a
loudness
slide that really
considerations get
shows
in.
why that is.
Okay.
I have a slide that shows why that is. Let's see how fast I can drop out of this one. Okay, the screen here, shop.
Well, while you're doing that, Bob, I mean, I'll put a little narrative back in for you so to give you a chance to do that. I mean, I think when we're doing measurements, any kind of irregularities can illustrate that there's something going on that we might not like. And, I mean, you don't expect to find jagged edges on things as you're going through, in this case, different frequencies and different levels. So it's surprising me, but what it means, as Bob says, who knows yet, right? But even at low levels, it's surprising what aberrations at low levels can do. And Bob, interrupt me as soon as you've got something to interrupt me.
No, you're doing fine. You're saying exactly what I would be saying.
And I mean, the one thing that I've spent a little time parallel to what Bob's doing is digital to analog conversion and looking at linearity of A to D's, D to A's, and it's fascinating what, how devastatingly obvious it is when a D to A, for example, doesn't have good resolution at the lower bits or lower dynamic range, because then all of a sudden it sounds bad, which is why a lot of the early CDs sounded bad, early ADs and D to A's. So I'm not as familiar with what Bob's doing, although I think it's incredibly cool. But where I've tried to dive in at depths like this, that's one place where I've seen those jagged little edges just don't do you any favors. There you go, Bob.
And the thing is, I'll say on the jagged little things, I'm not sure I understand them either, but the other one, the smooth surface, impressed me because I was not expecting to see anything that ever looked that smooth. And so maybe I'm just being unduly impressed because it's so unfamiliar to me. This is where are we for time? Okay, I can stretch it. These are just a few slides here. Block diagram of digital audio going out to a D to A converter, amplifier, the headphones, and the human auditory system perception and biases. And this is a presentation. I'm just gonna blow through a few of these, but it kind of answers that, why does it matter? Oh, I've got to be over here to, I'm just gonna concentrate on this part right here, from the amplifier through the headphones, the human auditory system perception, biases. And you saw that slide before, so we won't dwell on it. You saw that slide before, so you won't dwell on it. But what I'm going to say is, we're going from this kind of a slide here and saying this is where we begin our addition of all the things that change the signal on its path to our perception of what we're hearing. So we're talking about the music going through the amp after the D to A converter. I'm going to ignore the D to A converter, which is a whole big subject all of its own, as was just mentioned. And just say, take a look at our distortions and imagine, the dynamic behavior of the distortions. And then think of all the other amplifier performance that we can measure and do know about, which these include a lot of it. And then in keeping in mind that our electroacoustic transducers are not necessarily a benign load. They are sometimes very complex, and as the case of the focal clear. And then we start to add in the fact that the electroacoustic transducers have a frequency response, and they have their distortions. And so we add that in the path. So these are all summations of things that have been altering. Then we start with our own human auditory system, the ear canal, the ossicles, basilar membrane, and all the things like pinna size, ear canal, basilar membrane, and auditory masking. Then also important, where are we listening? And if we're listening at lower levels, suddenly things that we thought didn't matter at 40 dB SPL, and for the sake of convenience is why I like the Sennheisers, because they conveniently, one of the reasons, 0 dB U tends to be 100 dB SPL. And so if we're listening at, in this range right here, about 70 to 85, that's my favorite listening level. This is the fawn lines. But if we have a pause, or things like the decay of a note, or the echoes as it decays into the background, we'll be dropping down to here if our system is capable of reproducing it accurately. And so things that are 60 dB down, maybe even 80 dB down, we might be able to perceive as one thing. Everybody here knows JJ, I'm assuming. JJ points out that things going on the basilar membrane at one frequency and one band of operation can be quite different than on another band of operation. If you break up the basilar membrane, kind of like a crude frequency analyzer analogy, you could think that things going on one place could be at one level, maybe operating up here, and while other things are operating down here. And so some of these lower level events may not be as inaudible as we think they are. And then we keep in mind that the human auditory system has auditory masking, nonlinear behavior, and of course an individual may have damage. And then there's bias, personal preference, external influencers like noise in the environment, and even your mood. And when you stack all those things together, this is all the transformations that we go through, getting from the amplifier out to our perception of sound out there. So we start to realize it's very complex. It's not easy to just dismiss something because there's so many factors involved, of which even this one, this isocontours of equal loudness, is an average over many individuals and has been refined over decades. But any given individual may vary considerably from this chart. So that adds to the complexity. So with that, I'm going to go back to the other presentation. If you guys will stick with me here, and we'll finish up on that one. Where were we? We were about here. And if I say, there we go. We got a display on the screen now?
Yes.
Okay, good. This is where I think we left off. So here is another animation. This is the same information that you've seen before, but presented differently. What we're doing here is we're animating through the frequencies and giving you the sweeps. But in this particular case, we can have the THD plus N, the D2, D3, and 4 plus HD plus N all on the same visualization at the same time. So you can watch this thing. And as we go through the frequencies, watch how this spot right here drops as we go up in frequency. And that's a crossover between the D3 and the 4 plus HD plus N. That's an interesting behavior that wasn't as easy to perceive in those other distortion visualizations we've been looking at. I don't want you to get too confused by this too long. We'll go to the next one. Here is the Diablo DSD. And we see that the 4 plus HD plus N and the THD plus N is pretty much the same thing all the way through, and the D2 and D3 aren't much of a factor in there, but they might be. And then finally, this is the Molnar 3. And you can see that the 4 plus HD plus N is the factor that's contributing. And it's probably mostly noise, maybe possibly the ultimate dither, and then it crosses over to being D3 when we get, as we start approaching the power supply rails of that device. So these are yet another visualization. And it really takes a while staring at this before one starts to wrap one's head around the possibilities of what this offers.
Yeah, it's an impressive piece of work. I'm just curious if it was on your to-do list to do THD without the N and then 4HD without the N.
Yes, that's the, let me see about flipping way back here. This was discussed fairly early on, but I'm trying to get to that one. What I really want to get to is D2, D3, 4 plus harmonics only, just the harmonics, say 4 through 10. I don't think the higher harmonics are going to be much of an issue, but we'll start with 4 plus H. And then the N broken down into AC mains noise N and all other N, where the AC mains noise would be whatever if we're 50 or 60 hertz, since I'll be doing it here, it'll be 60 hertz. So 60 in the first 4 or 5 harmonics of 60 hertz, and then all other N. I'm programming the analyzer to be able to grab all that. Now, of course, this is going to change my 2-hour data acquisition to more like a 5 or 6 hour acquisition, and the 1 day to several days to create the visualizations. But I'm working on automating as much of that as I can, because the biggest limiting factor is there's a lot of data here, a huge amount. And as I'm creating these things, I'm an aging curmudgeon who gets confused at times. And when I'm looking at, say 100 graphics that are going to go into an animation that, or go together, and they're all named so similar to one another, and my eyes aren't what they used to be, I can make mistakes and bring the wrong bit of information into the visualization. So I'm trying to automate this to minimize the factor that I am kind of getting old. So,
Yeah. And
so
the other comment I had on the one with the wrinkles, I would be kind of interested. I realize this is a lengthy process to determine, but if you do 3 separate measurement runs or 4 on that device, are the wrinkles always in the same place or are they random?
okay, to that degree, every one of these measurements, there is a certain amount of noise in the measurement. And
course.
so what happens is during a measurement, we average the measure. As the sweep is run, we don't just grab the first one. It sits there and runs an FFT on it and averages that in the time domain several times, and then in the frequency domain several times. So we take a time domain measure. I was trying to get back to that crinkly one. So maybe I'm on this spot right here. We're at level, we're at the sweep of plus 5 dBu, and we're on the 5 kilohertz run. And we sit there and we run maybe 4 to 8 time domain buffers averaged together. That produces an FFT. Then we repeat that process 8 times so that we can really average the noise of the measurement out. So we should be able to get a fair degree of repeatability from measure to measure. And this is part of what makes the measurements themselves so lengthy in the real time, because of all those FFT averages. Maybe on another day, what I'll bring up is the D-Scope's parameter panel where I set all these things. And yes, this takes a long time to work all this out, to worry about such details, which is a great question. So I just wanted to leave you with, this is what my lab looks like. In fact, I'm sitting right here, right now in this lab facing this, except to my left, this 300B tube amplifier and the ABX blind measurement tester is not here. I have that Molnar 3 on there instead, and this DAC is not there. The successor of this DAC is sitting right on top of it. Other than that, this is what my workspace looks like, and I live a lot in this space here. I had when I was working for corporate, but now I'm on my own research using these tools for my own purposes. So that's what my space looks like. And one thing that's a little special about mine is I discipline my digital data with a rubidium frequency standard here, a Stanford Research atomic clock, and it runs at 10 megahertz, and it's disciplining this live clock. This MC3 Plus is when I need to do something really esoteric or weird and need to bring together 2 or 3 dissimilar streams. It's normally not even used. Normally it's just the rubidium disciplining the live clock. The live clock then disciplines the Focusrite Dante receiver. This takes the Dante streams that my audio lab is all based on Dante now. So I can send it everywhere, anywhere and everywhere. I've got 4 or 5 Dante sources and plenty of Dante receivers. And this converts the Dante to AES EBU, disciplined off of the rubidium. And it does matter. It does give me a very low jitter system to act as the source to my D to A converters. And then for the bench here, this is an EMI oriented bench. It's things are shielded. Even the power cords are shielded. And this is all run off of a true sine UPS. So we are really carefully managing our EMI field here, and periodically I'll actually go through and sweep this field and find out if I've had any new things show up here. Usually the new thing is me forgetting to leave my cell phone in the other room, so that brings in a problem. Or the Apple Watch that the smartwatch that I wear, it too will introduce a signal that can be detected in the field here. So that is this is the environment in which I'm working. I'm taking great care in everything that matters towards these measurements, and hopefully you found something new in what we've done here. And I'm going to stop sharing my screen so I can see everybody again here.
I can't wait to see some of the bad amplifiers.
Exactly.
Yeah, me too.
I'm kind of wondering what the output impedance of these amplifiers are. I'm not familiar with them in terms of driving your headphones.
Oh, every one of them is usually capable of at least getting the headphones, the electrodynamic ones, to 110, 120 dB. The only headphone that's really a huge challenge is the planar made by Hi-Fi Man, the HE6. The HE6, people claim you got to use standard speaker amplifiers on it. Really, what they're doing is they're getting an AB amplifier, Class AB amplifier, that's maybe 100 watts, and they're keeping it in Class A for a lot longer at a low impedance load. And that's all that's really going on there, is they're running in Class A, which I'm anxious to see that 300B triode amplifier and see if its surface it matches the one of the Molnar that I showed you. But yes, those are on my to-do list. But as you can imagine, when it takes me a day of focus to get each of these done, and some days I'm busy helping my wife with getting her through her things, as she's just recently had RSV and been coughing a lot. So the progress is sometimes a little slower than I would like it to be. First 6 months out of separating from the corporate, I was really looking after her, and I'm just now picking up steam again and putting the presentation together on work that I've been working on for quite some time.
What I was really interested in about the amplifiers, because historically, the first set of headphones I ever owned were some Koss, and it came with a little plug with a couple of big resistors in series with the loudspeaker amplifier output. And so the headphones were being driven with a higher impedance source than say a loudspeaker certainly would be. And so I'm kind of wondering, because the output impedance of the amplifier will affect the frequency response of the headphones. So
output impedance is one of the things we measure.
Okay, but as I say, for the 3 amps you showed, I was wondering what the neighborhood was for the output impedances. You were
those three,
that the headphones had nominal impedances of what, 32 ohms to maybe 600 ohms, or what?
Let's see if I can just, instead of the impedances of the headphones was one of the graphs in the presentation. Okay. And I'll put together a PDF and send it to Dan, and you can go back through and look through all these. What you won't get is you won't get the animations.
But we have it on video, and we can post the video.
There you go.
Okay.
The headphone impedances are on some of them are on the graph there, and they really fall into 3 categories. Electrodynamics are some nominal impedance with a rise of 3 or 4 to 1 at the driver's resonant low frequency resonant frequency, and the planars are smooth, usually all the way across. And then things like the focal, which is a little different. They've got a very underdamped. I don't know if I'm using the right term. They're floppy. If you work with them,
In
the
other words,
piston is really floppy, and it's got that huge 8.3 to 1 difference. But they all fall into roughly those, and so you could take their nominal impedance and just keep that in your mind. And then the output impedances on these things are typically some of them are 0.1 to 0.5 ohms. Some of them reach into the 1 ohm territory. I think the DSHA3F was 4.9 ohms. Then you get into things like the bottlehead crack, which is a do-it-yourself, build-it-yourself output transformers thing. It's got an output impedance of 120 ohms.
yeah,
It happens to work really well with Sennheiser HD600 and HD650. They are match together very well.
Okay. Now as I say, that's what I was sort of wondering about these amplifiers, because I've seen the advertisements from different manufacturers of 0.3 ohms output impedance all the way up to, as they say, 600 ohms, and maybe worse. And sometimes some of these amps have big fat kilo-ohm resistors from their final stage to the headphone jack. So, and I know that the resonance of the headphones reacts to that. The resonant impedance, which can vary all over the place, reacts to that. So
Most of the headphone amplifiers I've worked with are fairly low, and some of the tube headphone amplifiers that have transformer outputs have different taps for a high impedance versus a low impedance output, depending upon whether you want to use Sennheiser 300s or 300 ohm things, or whether you're dealing with 30 some ohm, usually 35, 40.
yeah, I know. And then
It's only the IEMs that get really low. Those little in-ear things, those things have some pretty low impedances.
Okay.
Well, thank you for taking some time to listen to this. Hopefully you found it informative. And like Dan says, I'm 2 minutes away from my absolute hard cutoff where I've got to go be there. So
Thank you, Bob.
okay,
It's really an honor to be among the first to see this.
you are among
Nice
the first to
job.
see it.
Thank
JJ
you.
got to see it a few weeks back. And yes, he had done something similar, not quite as involved as this, a couple of years back, or maybe many years back, but wasn't sure that the world was ready for this yet.
All right. Well, thank you. Have a good holiday gathering.
Thank you. And you guys have a good rest of your evening here.
Thank
You
you. We
too.
will.